Hi everyone, welcome. This is Amy Bailey from EDF Innovation Lab. Thank you for joining this webinar on thermal microgrids, a new opportunity for municipalities, universities, and corporate campuses to reduce energy costs and emissions. First, a few notes on webinar administration. We are recording the webinar. Links to the recording and slide deck will be emailed to registered attendees within a week from today. During the webinar, please submit questions in the chat window and we will answer all questions during a dedicated Q&A at the end. If you are connecting by desktop, directions to access the chat window are shown here at right. And I'll show this graphic again during the Q&A section. So here's the agenda for today's webinar. First, we'll hear from Sonika Chowdhury from City of Palo Alto Utilities, who will provide an introduction and context to the project.
Hello everyone, good morning. So I'm Sonika Chowdhury with City of Palo Alto Utilities. And before we start the webinar, I want to put in a plug for our project sponsors, APP, American Public Power Association. And we are thankful for this.
We cannot hear you.
Oh. So I guess I heard someone say that you can't hear. Could you please let me know, those in the chat window, whether you have sound, whether you can hear us speaking?
No, it's pretty much clear.
I'm sorry, could you say that one more time?
We didn't hear the beginning, but no, it's pretty good.
Okay, great. So we'll go ahead and continue, but please communicate via the chat window if there are any other issues with sound, or you can also go in and unmute yourself.
Okay, so first of all, we would like to thank our project sponsors, APPA, American Public Power Association, and their support for this project through their DEED grant. And City of Palo Alto Utilities, we are a small municipal utility located right outside the Stanford University campus, and also the located right here in Silicon Valley. So it provided us a great opportunity to collaborate with Stanford as well as EDF Innovation Lab, and you'll be hearing from our project partners shortly on the progress for this project. And I'll also put in one more plug for Palo Alto and our Palo Alto utilities. So Palo Alto has a very aggressive greenhouse gas reduction goals. So our city council adopted in 2016 that by 2030, we want to reduce our greenhouse gas emissions by 80%. And to achieve these goals, emissions from road travel or transportation sector, as well as emissions from natural gas, which are represented in red and blue colors in this graph of our annual emissions for many years. So those are two important components for our emissions for the city. And that's why for this project, it provides us a great opportunity to explore the thermal microgrid setup, which can help us for the building electrification. So with that, I'll pass on back to Amy for her presentation on this concept.
Okay. Thank you, Sonika. Our APPA-funded project has 4 total deliverables shown here, and this webinar covers the first 2. The first is a white paper providing an overview of thermal microgrids, including a description of the technology, economics, and opportunity. And the second one is a case study of Stanford's energy system, which is really the inspiration behind this entire project. Our presentations today are based on 2 written reports shown here, and the follow-up email will provide links to the full reports. So I see there are a couple messages coming in. I'm just going to break to chat to see. Okay, so it looks like some people are not able to hear as well. So I'll try to speak slowly and clearly. Thanks for sharing that in the chat window. Okay. We'll try this again. Okay, for a bit more context, the intended audience of the white paper is staff at municipal utilities, considering our APPA funding, or similar organizations such as co-ops, CCAs, investor-owned utilities, local government staff that may not have an electric utility, etc. And the key questions it addresses are shown here. For instance, first, what is a thermal microgrid? The advantages and disadvantages of them, costs, VHG, emissions impacts, etc. So we put the draft white paper together also, we put it through a peer review process, and we'd like to thank the following industry experts for their feedback. It was incredibly valuable having their perspectives to incorporate into this document. So thank you to you. The white paper will be finalized after incorporating feedback from all other stakeholders, including you, the webinar participants. As many of you on the call know, in the US, buildings are responsible for around 40% of energy usage and 1/3 of emissions. A large portion of this is from burning natural gas for space and water heating. Studies looking at technical feasibility. Studies looking at technical feasibility have indicated that substantial fuel switching in the building sector is required to achieve deep decarbonization, along with energy efficiency and continued electricity supply decarbonization. So electrification policies have been gaining traction, yet the current focus has been largely on building level appliance switch out. An alternative technical approach is to electrify an entire district. So district energy systems are networks of underground pipes carrying steam or hot or cold water used to heat or cool buildings, as depicted in the graphic at the right. Another term for district energy is local energy system. There are several advantages to district energy, including economies of scale from aggregating the energy needs of a cluster of buildings. Some waste heat recovery technologies or approaches may not be available or viable at a single building scale. And combining load and resource diversity enables you to optimize equipment sizing and enhance overall system efficiency. This project focuses on a specific type of district energy system, what we're calling a thermal microgrid, and we define it as follows. A thermal microgrid utilizes energy efficiency, renewable electricity powered heat recovery, thermal storage, and advanced analytics and controls to provide co-optimized power and thermal services to a group of interconnected and controllable energy loads within a defined boundary. Similar concepts have been introduced before, including renewable energy district and fourth generation district heating. The primary differentiators of this type of system are that it uses heat recovery as the primary heat source, as opposed to burning fossil fuel. It is a localized energy system that incorporates multiple energy carriers, such as electricity, heating, and cooling, as shown in the figure. And the entire system is optimized over all energy carriers. We use the term microgrid here to emphasize all the benefits associated with traditional electricity-focused microgrids, such as local energy utilization, enhanced community resilience and reliability, systems optimized control and dispatch, and the ability to meet critical loads during larger grid disturbances. The adjective thermal in thermal microgrid is added to denote that the microgrid also incorporates thermal services such as hot water, steam, and/or chilled water, in addition to electricity. And as mentioned before, this concept is inspired by Stanford's energy system. The same three trends that are disrupting the entire energy sector more broadly are responsible for increasing interest in thermal microgrids, specifically decentralization, decarbonization, and digitization, all of which are prominent features or attributes of thermal microgrids. Decentralization in this case refers to the transition to a local grid paradigm. Decarbonization is moving from a fossil fuel-based energy system to one that's sustainable And digitization is referring to the increased deployment and utilization of sensors, control, and AI. When evaluating whether a local energy system is a viable option for a community, there are several sometimes competing considerations, a subset of which are shown here, such as economics, of course, environmental impact, reliance on fossil fuel, etc. In order to evaluate a thermal microgrid versus alternatives for their community, stakeholders in the community must first identify and prioritize their goals and objectives. Public power, or munis for short, are uniquely positioned, we think, to lead investigation of thermal microgrids. For instance, electric and thermal utility services can achieve cost savings across an electric and thermal utility through, for instance, coordinated trenching. Munis are in a position to standardize interconnection processes and develop innovative policies that harness value. And successfully deploying such a system requires the ability to navigate complex multi-stakeholder processes, which munis have been doing for decades. And historically, public power has shown leadership on environmental issues. So now I'll go through an overview of the technology. So there are four main components to a thermal microgrid, or more generally, a district energy system. First, there's the heating and cooling sources, including thermal storage, which is the central equipment, which is labeled in the graphic by the circle with the number 1. There are a variety of different low and high grade heat sources that could be used, which depend on the location of the system and availability of the resources. The focus of thermal microgrids are heat recovery opportunities, which a large untapped resource is waste heat recovery from buildings, which is a focus of Stanford's system, which you'll hear more about in a bit. There are also a variety of ways to produce cooling for a district energy system by combining heat sources with heat pumps or from surface water, for instance. And thermal storage, in addition to heating and cooling sources, is a technology that can be incorporated into the system design to cost effectively increase heat recovery, load shift off-peak periods, enhance resiliency, and reduce the capacity requirements of other central equipment. The second is the power source, either located remotely or on site. And I won't go into detail of that in this webinar, since many participants are already very familiar. So the third component is a thermal network or distribution network from the central energy facility to the buildings. And this is the analog to the distribution system in the electricity sector. So a thermal network is the distribution network of pipes, substations, valves, and controls to deliver steam, hot water, or chilled water from a central energy facility to end customers. There are 3 types of thermal networks. For some systems, it's a heat network, where you're providing heat directly to the buildings, but you can also provide cooling at the building via absorption chillers. A cooling network is a second type of network, or a tempered water system. And similar to an electricity grid, thermal networks have network operators and control outgoing water temperature and regulate flow to ensure all the customer needs are met. The fourth and final component is the building interconnection equipment to couple the thermal network to the building heating and cooling system. And there are 2 types of interconnection types with customer buildings, specifically a direct connection where the energy carrier is pumped directly through the building heating and cooling equipment. And the second type of interconnection is an indirect connection where the thermal network is coupled to the building via a heat exchanger. And typically, the building interconnection equipment incorporates controls, heat meters, isolation valves, and filters as well. Excuse me. Like other major infrastructure projects, thermal microgrids have substantial fixed upfront costs. Nonetheless, the system may lead to substantial offsets, costs that would have otherwise been incurred by maintaining the existing system, such as transmission or distribution system upgrades. The three main cost categories are shown here. And the final cost, of course, will depend on the system design, local system conditions, and other project details. For illustration, this figure summarizes the results of the economic assessment of multiple central energy replacement options from the Stanford case study. Along the horizontal axis are all system design options considered, categorized by power source, heat network, and level of heat recovery. And on the left vertical axis is present value costs in millions over the anticipated system lifetime, and costs are broken down by four sources: electricity, natural gas, O&M, and capital. Water usage and GHG emissions are also plotted along the right vertical axis to reflect the environmental impact of each system design option. So this figure is specific to Stanford's detailed evaluation of replacement options for their cogen plant, but the relative trends between energy system design options are transferable to other locations. The primary drivers of feasibility of these sorts of systems are listed here. The first is load density. The thermal network is expensive, so the closer the buildings are and the denser the load, the more cost efficient it will be. Second is the cost of the heating and cooling supply. Advanced heat recovery enables low-cost source heat in the thermal microgrid design. And another feasibility driver is load diversity, where the greater the load diversity, the greater the potential for optimization across the local energy system. There are a variety of existing energy and climate policies in various regions that would promote thermal microgrids, such as carbon taxes, cap and trade programs, energy efficiency targets, such as California's doubling of energy efficiency by 2030, and local air quality standards. Nonetheless, there are also many non-technical market barriers, such as those shown here. For instance, a lower familiarity with district energy in the US, parts of the value chain may be underdeveloped, complex multi-stakeholder processes for infrastructure development, etc. A comprehensive quantitative potential assessment is the subject of ongoing work. There are a variety of business models available for thermal services similar to those in use for municipal electric utilities. For example, an enterprise fund and operational department within a university or local government, which is how Stanford and Palo Alto utilities are structured, special districts, cooperatives, and a community-owned LLC. There are also non-municipal business models as well, which are not listed here. So in conclusion, decentralization, decarbonization, and digitization are driving the transformation of the energy sector and interest in thermal microgrids. The same drivers have spurred interest in this particular project. Stanford's system demonstrates the potential of thermal microgrids for achieving decarbonized, cost-effective, and resilient local energy system, which you'll learn more about in a minute. And although there are several non-technical barriers that challenge market transformation, we think that munis are in a very unique position to lead in the deployment of these systems. Okay.
Hi, this is Joe Stagner, Executive Director of Sustainability and Energy Management at Stanford. I'm going to repeat some of what Amy said quickly and show you how our system works. We've transformed our small city of 30,000, I like to call it, to this new system. It's been operational for over 3 years. I had independent audits to prove the economics and performance of the system, and it continues to run well. Repeating what Amy told you, but providing a cute little pie chart, buildings are, 40% of the energy consumed in the Western developed world, and a like share of emissions of greenhouse gases, as well as other more, serious priority pollutants. And of that, electricity, heating, and cooling consumed by buildings, the vast majority, half to 2/3, is for heating and cooling. So many of the industry directions on energy efficiency in buildings and moving to electric microgrids are great, but we want to make sure people don't overlook the largest of all opportunities, which is thermal. For instance, at Stanford, we toiled for 10 to 20 years to achieve a 20% reduction in energy use in our buildings through building side energy efficiency programs. And in 5 years, we cut our energy use in half with this new thermal system. So energy efficiency in buildings is great, but revising the thermal system of how individual or buildings collected together in district energy, how that energy is supplied by the techniques we're going to show, are far faster and far larger opportunity than energy conservation or electrical microgrids and related, and I'll show you why. The other thing of note is it's in the last 10 or 15 years, as folks look to reduce carbon and understand things, it's become quite clear that there's really only 3 paths to sustainable building energy. I'm sorry, Amy's doing something here. I'm trying to figure out.
If everyone can please mute yourself, I think we have one person unmuted.
Okay. After that note, then back to the slide. So there's really only 3 paths to sustainable building energy. We can continue to use carbon fuels, but we have to do carbon capture and storage, or we have to use sustainable biofuels. Carbon capture and storage isn't effective. It's not cost effective. The technologies aren't there and may never be there. Any of you that have looked at that know carbon capture and storage is only used in about a dozen places in the world, most of which are oil fields where they re-inject carbon to push more oil out. They tried to build a giant carbon capture and storage clean coal plant in Kemper, Mississippi, and it's turned out to cost about 5 times as much as a new nuclear plant, and it still doesn't work. The opportunity or thought that somehow carbon capture is going to move down to a small scale like a district energy system or a house or a cogen plant serving a corporation, that's likely never going to happen. It's way too expensive. And even if somebody does invent a machine that'll capture all the carbon off your smokestack, trying to get that carbon somewhere where it can be put in the ground safely forever, that's, of course, very impractical. So there's no catalytic converter that we can rely on to make our way out of using carbon in furnaces at our houses or boilers in our buildings. Sustainable biofuel is more practical. We can keep our carbon fuel combustion devices if we can feed them with clean fuel that's actually environmentally sustainable. But the scientists will point out that's not scalable. On the global scale, there simply is not enough land on the planet to both grow food to keep our population fed and grow crops, as it were, or algae or anything else that we can turn into biofuel. And it's far less efficient and more costly than, say, putting a solar panel up or a windmill. So we're not real high on the thought of trying to continue to use combustion of carbon fuels and capture and store the emissions or avoid them through sustainability. It's really not practical, but for all of very few people that can do sustainable biofuel. Well, then you've probably heard about the hydrogen highway, right? Companies producing hydrogen fuel cell cars and stuff. If you produce hydrogen by using clean renewable energy to split hydrogen off water through hydrolysis, then you have a sustainable energy system. But as it turns out, it takes twice as much renewable energy to split hydrogen off of water and use the hydrogen to drive, say, a car, as if you just put renewable energy directly into an electric car. So You can use 1 kilowatt hour to drive your Chevy Bolt or Nissan Leaf 3 miles, or you can use 2 kilowatt hours to have a clean hydrogen car go 3 miles. So hydrogen appears to be far less efficient and more expensive than just going with clean electricity. The potential homes for hydrogen are in devices, transportation that cannot be electrified, and that's airplanes and ships and perhaps long-haul trucking. So that's why a lot of research continues in that. Although Tesla's come up with a short-haul semi option, for instance, apparently long-haul semi still would require too big a battery that weighs too much to be able to go great distances. And so some compact form of sustainable fuel other than a battery may be the next best choice than continuing to belch out all the diesel. And hydrogen, for instance, may be a solution for trucks. I don't know if it'll ever be a solution for aircraft or not, and or ships, but that's why research continues around hydrogen, but I wouldn't factor on using it for all of our regular transportation or our buildings. It's far less efficient and far more expensive than the middle option, which we did and which a lot of folks now recognize as the best, and that's electrification plus renewable electricity. It's the most efficient, lowest cost, it's eminently scalable. We already have a nationwide and worldwide distribution network to get electricity to almost every corner, and it's far more flexible because you can produce clean electricity so many ways today, and there may be so many other ways in the future. So in summary, clean electrification with renewable electricity is doable now. It can be done fast, and it's the best long-term option as far as we can tell. But don't take our word for it. In 2009, we reached this conclusion and developed our system, which was approved by our board in 2011, and we started to build it, and it's been operational for a few years. 2011, the International Energy Agency came up with the same conclusion that we need to heat and cool our buildings with clean electrification and heat pumps. Deep decarbonation studies sponsored by a number of institutions and performed by a couple national labs came up with the same conclusion in 2014. The United Nations, same conclusion in 2015. And more recently, Southern Cal Edison in November of 2017 published their study of how they can help get to California's greenhouse gas reduction goals. And they looked at the exact same 3 pathways: hydrogen, clean carbon, and clean power and electrification. Their study shows clearly clean electrification is by far fastest and cheaper. And here's one of the reasons for that and one of the ways you can do it. So we can make electricity clean and supply power to our buildings, and then we have sustainable power and lights. That's pretty easy. Most air conditioning is done with electric machines. And so if you clean up the grid, well, you've got clean air conditioning by and large. So the real challenge for society is how to provide heating and hot water cleanly. Producing heat with natural gas is a lot more efficient if gas is the only fuel one had to use than doing it with electricity. So in the top, you can see if you were to use one of these electric radiant heaters or an electric water heater at your house or building, assuming you have a 50% efficient grid gas power plant, which is the nominal efficiency for electricity made with gas. And as a lot of you know, a big part of our nation is moving to natural gas powered electricity and renewables, natural gas being a big component. So if you put 6,800 BTUs of gas in a grid power plant, you get a kilowatt hour electricity sent to your building, and that'll make 3,413 BTUs of heat. But if you, instead of sending that gas in the grid gas power plant, you just put it in a boiler or a furnace at your house or building, well, you can use 1/3 less gas and get the same amount of heat. So that's why there's not a lot of electric homes and buildings anymore, because if you're going to burn gas, might as well burn a lot less and do it with a boiler or furnace at your house. But the new thing that's even an order of magnitude better than that method is an electric heat pump. So going back to electricity, but instead of using electricity to make heat by just heating up a piece of metal, an electric heat pump can do it with 1/4 to 1/2 the energy of even the gas situation. And the reason that is because a heat pump, unlike the other 2 methods, does not transfer energy into heat. Rather, it consumes a little electric energy to take heat from one place, package it up in the form you need it, and deliver it to another other place. So for instance, your home air conditioner is an electric heat pump. It basically takes heat you don't want in your house in summer, and it transfers it out the side of your house via the air-cooled condenser. Big chillers at buildings are the exact same process. They take heat out of the building and they put it out in the evaporative cooling tower that also consumes water. Well, instead of wasting that heat through evaporative cooling towers or out the side of your house, what if we turn that heat into hot water that could be used for clothes washing, bathing, cooking, and for those buildings that need heat into heating? So just a little bit extra electricity into that chiller, and you get what you call a heat recovery chiller. It's just like a regular chiller. It's just that instead of putting 95-degree water out to go to a cooling tower to get rid of it, it might make water that's 120 to 170 degrees that you can then use in all modern building systems. So the electric heat pump is the key to unlocking electrification of this 40% building energy section for the world. And that's why Stanford went to that. So the next question is, well, I can use an electric heat pump, but how much heat could I recover from my air conditioning process? And then where would I get the rest of my heat? So let's talk first about the heat recovery process. So these three charts show Stanford's typical heating and cooling profiles on a daily basis for summer, winter, and then the in-between seasons of spring and fall. So on summer, you can see we have a lot more cooling in the daytime when the sun comes up and than we do at night. We have a constant demand for heating and hot water for bathing and many other things. In winter, it's the opposite, much more heat demand than cooling demand, and in between the spring and fall. But those green areas show when we have this overlap. So if you think of a cooling system not as a system for delivering cold, it's really a system that collects heat. It's a system that collects unwanted heat and then it does something with it. Today, we typically throw that heat away. So this overlap is of a system that collects heat and one that delivers heat. So obviously, if you're collecting a bunch of heat in your air conditioner or your central plant, rather than throwing it all away, why don't you reuse as much as you can to meet your heating demand and only throw away what you can't use? And this green depicts that opportunity. If you look at it over the course of a whole year, here's what Stanford's cooling and heating profiles look like. Above the x-axis is our cooling demand profile, and you can see obviously much more cooling in summer than winter. And likewise, the red below the x-axis is our heating demand profile, and of course there's more in winter and less in summer. When you do the overlap, you can see how much of that waste heat in blue that we had been throwing away in cooling towers we could now turn into hot water and use to meet our heating loads. 53% of our waste heat supplies 88% of our annual total heating demand on campus now, meaning 88% of the fossil fuel that we used to burn in furnaces and boilers to make heat, we can now make with our electric heat pumps. And it's really a byproduct of something we've got to do anyway, which is cooling. So it's almost like free heat. There's a ratio of 1 to 1.4 because the heat you take in to throw away, the electricity that runs the machine to do that, the heat pump, is converted to heat as well, and it's added to the heat you bring in to throw away. And so you actually get about 1.4 units of available heat out, in our case, for every 1 unit of waste heat you're trying to get rid of. For those of you familiar with basic energy systems, especially at the district level, this is just a reference diagram that explains the differences. So there's the three services we need to do for buildings: heating, cooling, and power. Now, a lot of you heard about cogeneration plants or combined heat and power, and that's diagrammed on the left. You put fossil fuel, most notably natural gas in most places, into a cogeneration unit, which is typically a gas turbine, like a jet engine on a wing. It produces heat and electricity, and then you use some of the heat and electricity to drive steam or electric powered chillers to do the cooling part. The trouble with that system and the system Stanford used for 25 years is it's all fossil fuel. It's 100% fossil fueled. Typically at your house or at many simple buildings, you have what's called separate heat and power. So at your house, you'll have a furnace that burns gas probably to make your heat. That's designated in the red box. You'll have an electric air conditioner that does your cooling in the middle, and you'll get your electricity off the grid in yellow. So you're getting your heat and power from separate sources, and that's what's used anywhere there's not a cogen plant, typically in the country, from your house all the way to a district energy system. Well, this new scheme we call combined heating and cooling is shown on the right. So we get two products out of one piece of equipment, our heat recovery chiller. We get heating and cooling out of it. On a cogen unit, you put in fossil fuel, you get heat and power. The heat recovery chiller, you put clean electricity in, you get your heating and cooling. And then you have to get your power from somewhere else. But since you're getting all clean power from windmills, solar plants, whatever, then the whole scheme is electrified and it's all supplied with clean electricity. And it turns out, as Amy showed you our economic diagrams, and I could show you thermodynamic and energy efficiency diagrams, the system is also far more efficient than any of the other systems, including cogen, which everybody in the country, or a lot of people in the country, think is still the most efficient way to do things. It's only because they don't know about combined heating and cooling. When you actually look at the figures, combined heating and cooling is far more efficient, and that's because it does something cogen doesn't do. It's reusing energy that the cogen system throws away. So all of that heat that we took in our cogen plant all year and threw away in evaporative cooling towers, we're now using that. So about 1/3 of our energy is now free, and we don't have to burn gas to get it. And so that's why the efficiency of a combined heat and cooling system or a thermal microgrid is untouchable from any other technology. And the fact that it's electric means it's a pathway to sustainability too. So the basic overall components, whether it's at your house or whether it's at a commercial building or a district energy system, is the central part is a heat pump or a heat recovery chiller. And again, it's just the same thing as a chiller. It's just that it puts out a little bit more hot water than a chiller might, because we want to make the water hotter to use instead of just enough to evaporate water in a cooling tower. And then for that portion of air conditioning in summer where you don't have a place to use the heat because already 100% of your heat's being provided by your waste heat, you still have even more waste heat because it's hot in summer. Well, you can then throw that away like we have thus far through evaporative cooling towers or inject it into the ground or what have you. And so you'll need a conventional chiller to do that because it uses less electricity than a heat pump to do it. You don't have to heat, fluid up to 170 degrees via heat pump to send it to an evaporative cooling tower. You can use less electricity and only raise the temperature to 95 to throw it away. So it's more efficient to use the chiller for throwing waste heat away than the heat pump. And then a boiler or hot water generator, which supplies the balance of your winter heating that you can't provide through your own waste heat recovery. And typically you'll probably put in enough capacity so that if the grid went down and you didn't have your heat pumps to make heat, you could burn gas in your hot water heater to get you through those few hours of that or day or two. Optional and highly desirable to add to those three, you could have a system just with the top three do just fine and make lots of efficiency and cost improvements for you in greenhouse gas and water reductions. But if you want to make it even better, hot water thermal storage, cold water thermal storage, and what we call model predictive control software will help you get another 20 or 30% efficiency and cost savings, and I'll explain how those work. Here's a diagram then of the plant we constructed to do all the heating and cooling for Stanford. So referring back to our heat recovery chart, you can see the big goldenrod color in the middle, the heart of the system, which does most of the work. We have 3 heat recovery chillers that do simultaneous heating and cooling. We have hot and cold water tanks so that we can store heat that can't be used in the day to use at night or later, so we can have less total mechanical equipment and have all the benefits of thermal storage that Amy pointed out. And then we have our conventional high efficiency gas hot water generators and electric chillers and cooling towers to handle that balance of blue and red you see on the chart that we can't do with heat recovery. Now, to fully eliminate all gas use and increase the efficiency of any system like this, you can use those heat pumps in winter and suck heat out of the ground or a body of water, or even the air if you wanted, so you don't burn gas to make that red part. We've designed a ground source heat exchange system of wells we could put in the ground and circulate water to allow the heat recoveries to suck heat out of the ground in winter. And we're also exploring using our campus irrigation system and several small reservoirs, lakes of water on our property where we store water for summer irrigation. And that's probably going to be preferable as the place to exchange heat with in summer and winter. And then the ground source system will be secondary due to economics. But so that blue and red for us will be moving to full electrification as well. So we'll be 100% carbon free when we do that. So this model predictive control software, think of it as an autopilot for an aircraft. When you have a system like ours where you have hot and cold thermal storage, heat pumps that do both heating and cooling, chillers that do just cooling, and boilers or hot water generators just as heating, you have these 5 energy components that can all do work to meet your load. Humans can decide how to run those and meet loads, but a computer can do it faster and more efficiently. So we developed this system where we can predict what the loads will be every hour for the next week at any given time, based on what the weather forecast is, and past information on energy use from our campus. And we predict what electricity prices will be. It could either be your electricity tariff if that's fixed, or if you're on open market, what we call direct access power here, it's whatever we think the market prices will be. So we have algorithms that predict that. And once you put in what you think your loads are and the prices of electricity on what days of the week and what times of the day, the machine then figures out the optimal way to dispatch or run all this equipment and when to take and put from thermal storage to meet your needs in the cheapest way possible. And so we did a test where we had our control room operators show how they would dispatch the plant to meet a year's worth of loads, and we compared that to how the computer would do it. On the left are the results. So again, we have basically an electric system, and the squiggly red line is how much electricity our buildings use. And then the orange line is how much more electricity we use to do our heating and cooling with our new energy plant. So you add the electricity the buildings use and the electricity our central thermal plant uses, and you get the orange line, which is the electricity profile we present to the grid, the electricity we buy off the grid and the pattern for that. You can see on the right that the computer has a much more stable and lower peak profile, which is actually uses 7.3 megawatts less peak demand than if the humans did it, and it saves us about $500,000 a year in electricity costs, or about 10%. So this model predictive control software is a great thing to use to plan systems and then to actually operate them like an autopilot, and that's what we use it for. It's a very quick payback of this software, and it increases reliability and saves a lot of money too in applying advanced mathematics to do things that humans can do, but just not as good. I mean, a pilot can fly a plane from San Francisco to New York just fine, but an autopilot can even do it a little better. So as Amy pointed out, systems like this work great in district energy, and there's a lot of reasons why for cities, whether even residential like they do in some places in Europe, to more dense building sectors like downtown parts of cities or universities, district energy can do things more efficient than having a separate air conditioner and heater in every individual building. It saves a lot of money on capital, allows for a lot of diversity of load. For instance, a building on one side of the street might have excess heat on a given day, and a building on the other side of the street might be short of heat and then be turning its heater on to make heat for itself. Well, if the building across the street could get rid of its excess heat by giving it to the building across the street, that saves burning fossil fuel, that saves money for everybody. And that's just one basic feature of why district energy is such a good thing. These documents from United Nations and others show why district energy is good and all the benefits. But again, all these concepts we've talked about, you could apply from your residence all the way through district energy. A lot of folks, when they saw our system, particularly those in colder climates, thought that this was a left coast Palo Alto thing, that it's only our mild California weather that allows us to do this stuff, and it would never work in New York or Chicago or someplace cold. And that's really a myth, and we've proved that. And it's a myth because if their main concern was if the grid goes down in an ice storm or snowstorm and we're freezing, how possibly can we stay warm with this electric heat recovery deal? Well, the fact is the grid only goes down a few hours per year in most places. There's lots of news events, and yes, some places every 5 or 10 years might be out a day or two. But if you look at the federal government data on the average electrical grid outage across the country, you can see that it's only an hour or two every year. So, why construct a system that you're going to operate for the next 30 years to be 100% fossil fueled so that maybe once every 10 or 15 years you have protection against a grid outage, when indeed the electrical system like ours provides that same protection plus more. So we can make heat, keep our buildings warm 4 ways. We use electricity 99.99% of the time because that's when the grid's up and it's available and it's cheaper and more efficient and cleaner. We have, if the grid goes down though, we have thermal storage. So there's going to be some hot water in a hot water tank that could keep us going from a few hours to a whole day, depending on when things happen. But even if those fail, then I have everything a cogen plant or a conventional system does. I have enough natural gas heaters and a big pipe of natural gas coming to our campus that I could heat continuously our campus with natural gas for as long as the grid's down. And our units also have liquid fuel and tanks. So if the natural gas network goes down because, say, the grid was out of power and that stopped all the natural gas transportation pumps, well, we can use liquid fuel. So we actually have 4 ways to make heat, whereas cogen and conventional systems only have 2 ways to make heat in cold climates. So it's a myth that an clean electricity-based heating system is less resilient or less efficient in cold climates. It's actually more efficient and resilient. This also proves the fact that it's not just mild climates where heat recovery works. Upper left is our heat overlap chart. Upper right is our new Stanford Redwood City campus. Now we're in the same weather, right? Mild climate, but it's a totally different type of building community. It's a Monday through Friday day shift only operation of administrative folks. So it's a much higher cooling demand over the summer than heating because it's not open nights and weekends. Yet still 57% of the total heat used by that facility over the course of the year will come from its waste heat. Lower left is the University of Illinois. They use about twice as much energy as Stanford because they're bigger, and you can see their wintertime cooling loads are much dramatically bigger than Stanford's. And it's true that in the dead of winter, heat recovery cannot provide most of your heat, but it can provide all of your heat in summer and part of your heat in spring and fall, and an even smaller portion in winter. Over the course of the year, 55% of the heat consumed by the University of Illinois could be supplied with their own waste heat they're throwing away now. On the lower right is the University of California, Davis. They're in a climate that's much colder in winter and hotter in summer than ours. Again, 50%. And when you look at these, it makes quite a bit of sense because everywhere in North America in summer, we have a surplus of environmental heat. And almost everybody's doing some form of air conditioning, which is collecting and throwing away heat. Why anywhere in summer we would burn fossil fuel to make heat for hot water or washing clothes or anything, it just makes no sense. We don't have to do that. And these charts reveal that that's the case everywhere. Final slide then kind of reaffirms somewhat of I and Amy have talked about, that it's important to increase the efficiency of buildings, and there's a lot of talk about electric microgrids and perfecting an electric microgrid and this and that. But the lion's share of the opportunity for sustainability, efficiency, and economic savings is in thermal microgrids. Taking that 2/3 of our total building energy that's done for heating and cooling and finding a better way to do that more sustainable, and that's what these systems do. So this chart diagrams that concept. In pink is our thermal microgrid, our system. It considers the electricity used by the buildings, but primarily most of the savings are on how we heat and cool and convert that to electricity. When we now add on-site PV, and we've added 5 megawatts to our rooftops, we're starting to get more plug-in electric vehicles, and we've studied heavily and may or may not add electricity storage. Those typical components of the quote electrical microgrid, they have value, but they're not nearly the opportunity of the thermal microgrid. And the point is really we should look at all of them and think of a total energy microgrid, not just an electrical grid and not just a thermal microgrid, which most people don't know about, and we're trying to share with you the importance of, but look at the whole thing. Thermal should come first because it's the biggest opportunity, it's the fastest conversion, most money to be saved, etc. But also do electrical and really think of it all together as a total energy microgrid is our advice. And with that, we'll turn it over for Q&A.
And just one more comment from me on next steps before Q&A. This project team has 2 more deliverables, as we showed you earlier on. A suite of tools to aid muni staff in assessing the techno-economic feasibility of thermal microgrids for their service territory, and applying those tools to a region of Palo Alto and a region of another muni outside of California. We haven't actually confirmed a second muni yet, so if you are a muni and interested in assessing part of your service territory for a thermal microgrid, please contact us. And also, we will organize another webinar in the fall or winter this year to share the final results from the project, so stay tuned for that. And so now for Q&A, and I'll turn it over to Sonika to lead the Q&A portion.
So, the Q&A part, so if you have any questions, you can unmute yourself and or type in your questions. And I'll start with some of the questions we already received in the chat box. So first one is for you, Amy, from R. Schmidt, and maybe we might need clarification on this, so if you can type in that. So the question is, I think some of the results you have shown are these kilowatt hour per square feet, and are these across Europe and US?
Yeah, so I'm not sure exactly what this question is under the technical feasibility. There is a metric around 0.9 above that, thermal loads are building out of the, and so I believe that that's but I'm not positive. So maybe chat window, if you could provide some clarification, we'll come back to that. Thank you.
Okay. And Amy, I'm getting again this notification of lost sound. Okay, we'll continue. We'll see if it works now. And any other questions from the audience? So if you have any, please type in your questions. I'll also write this. So kilowatt, so another question from the audience on the similar topic, Amy, kilowatt hour per what period of time and all geographical area? That's the question. Follow up to your response.
Okay. So that's the thermal, a single method that's quite simplified. And what that's saying is if you have a cluster of buildings load on average for the first 3 years, then likely viable. However, it's really and so I would consider it, kind of a very prior to evaluating whether this sort of system would be viable.
Sorry for the sound problems. I think we are still getting lots of notifications. So on the Q&A questions we get here, we can also maybe type in the responses here. And before we end the webinar, a quick question from the audience. So it is related to like what's been the economics of the project since the project has been now, and how do you compare it with your own system?
So the efficiency of our system thermodynamically is twice as good as the old cogen plant. So the only way you compare the efficiency of a gas and electric system or a system based on gas and coal and electricity, different kinds of fuels, is to pick a common fuel. So we asked the question, if we were to burn natural gas to make all the electricity to drive our system, how much total gas would be burnt to make electricity on the grid and or on our site compared to how much total electricity was used with our cogen plant on site and a little bit imported from off site. And we use half as much total natural gas today as we used just 5 years ago with the cogen plant. So our efficiency is doubled. That's a result of both newer equipment, but it's primarily the result of a much more efficient system where we're using energy instead of throwing it away, the waste heat like the cogen used to do. As far as economics, you saw the bar chart pro forma. And with 5 different peer reviews from outside entities of economic and thermodynamic models, we predicted for the next 35 years that this system had the lowest overall cost. But if you recall that bars and bubbles chart of the capital O&M and electricity and gas, it also became clear that for the various gas-based systems like cogen versus the electric systems, that the net present value over 35 years was all within about 10%. You know, we're from 1.2 billion to 1.35 billion estimate. So strategically, when our board and others look at it, you say, look, I got any of these 9 systems I can build. They're all within 10%, which is within the tolerance of error of predicting what gas and electricity will cost the next 35 years. So unless there's a giant economic winner that's clearly, 30 or 40% better than the others, I'm going to pick the clean, flexible, sustainable electric one. Why would I build a new cogen plant that uses natural gas and be stuck with that for 30 years? But I can go with a much cleaner, more flexible electrical thermal heat recovery system and have all kinds of ways to supply electricity over the years, including what we ended up doing, which is locking in cheap prices for clean electricity via a 25-year solar purchase. We know what our budget and costs are going to be, that energy is going to be clean for the next 25 years. So we get budget stability too. So we've had a third-party audit after the first year of operation by a company called Navigant for our board to check, is our system delivering on its promises? And after 1 year, that audit proved that yes, it's slightly more efficient and 10% cheaper than we thought, because we've got direct access to electricity markets and got cheaper power, both regular market and the solar PPA. After 2 years, we've redone all the figures, and it continues to exceed our economic and sustainability pro forma that was approved by our board in 2011. So yes, we're very transparent with all of our data. We've had multiple peer reviews, and this data is available for anyone to see, but it is more efficient and sustainable and economic than we even thought.
I think we have time for one more brief question, and we have a question about seasonal storage, whether that's been considered. And so maybe Joe, you can comment on
Sure.
your system.
So as you see from our system, really 50% at least of everybody's heat can be made through heat recovery. You don't have to worry about seasonal storage. But what about that balance? So in our case, our underlying groundwater moves, and so we can really take a foot from our ground anytime we route without worrying about balancing the BTUs of energy taken in winter and deposited back in summer. Now, some places, especially the Midwest, the Illinois, places like that, you don't have moving groundwater, you just have perched soil or water. You have to balance the BTUs, you take it out in winter and you deposit back in summer. So you just have to model what you need to do. So after you do all your heat recovery, if you recall that University of Illinois overlap chart, you look at how many BTUs you need to suck out of the ground in winter and how much you can put back in summer, and you work the balance. If there's not enough waste heat in summer to put in the ground and take out in winter, then you might have to get more heat from a body of water or suck it out of the air, or maybe burn natural gas. So yes, you do have to consider for the non-heat recovery part, your subsurface, and whether you have moving groundwater or whether you have perched soil groundwater, you have to consider seasonal balance.
Okay, and we're at time now. I apologize for the technical difficulties. Thank you all for kind of suffering through that with us. So we will distribute a link to the recording and also the slides to the registered participant list after the webinar within a week. And if the sound quality is off, perhaps we can consider a voiceover or some other option for making sure that you are getting the information from the webinar. Thank you very much. Bye-bye. Thank you.